Hey there, this is Arna from Pebble, and welcome to the Introduction to Linear Algebra. This is a brand new course developed by Pebble Education that will go through all the core concepts you need to understand linear algebra in a format that's hopefully understandable to a wide variety of people, including people from a high school background or people who may need a small refresher and have already encountered these concepts before. So in this video, I wanted to talk about a few types of special matrices that you'll see pretty often in linear algebra, and I have to kind of dedicate a whole video to them just because they appear so often in linear algebra. And I'm also going to throw in a little section at the end about linear systems and how linear algebra can be used to represent that. And I feel like that should be pretty good to leave you off on in the first video. So without further ado, let's just get right into it. So special matrices, the first one I want to talk about is called the transpose. So I'll write that up there for you, transpose. And I'm assuming that you already have prior knowledge and experience with matrices, so this is going to be pretty simple. The transpose of a matrix is just, let's say we have a matrix 1, 2, 3, 4. And I apologize for my handwriting in advance. 1, 2, 3, 4. And the transpose of this is basically just going to be whenever we swap the rows and make them our columns. Okay? So the way this would look, and the way we note transpose, is A with the superscript T. And so we swap the rows and make them our columns. What does that mean? Well, the first row, 1, 2, becomes our first column, and then our second row, 3, 4, becomes our second column. And this would basically just be our transpose. And transpose is pretty useful in a couple different applications that we'll see later on in the series. And the transpose also works with matrices that are not square, so you could have a 2x4 matrix and the transpose would still work for a 2x4 matrix. So the next type of matrix extends off transpose. It's called a symmetric matrix. And so symmetric matrices are whenever they equal their own transpose. So let's take a matrix like, and obviously this applies to any size. Let's take a matrix like 1, 2, 2, 4. Or 1, 2, 2, 1, actually. So you can kind of see how this would already look. This kind of looks symmetric, but just to show, the transpose of this, well, let's do this again. First column becomes our first row. Second row becomes our first column. Second column, sorry. And transpose, just like that. And you can see the matrices are the same. And if I were to change this to a 4, that would mean that this would change to a 4, and they would still be the same matrix. And that's what makes it symmetric. Okay? And the next type of matrix that we'll want to see is called skew symmetric. And this one, while symmetric is pretty common, you'll see it a lot in some of the applications of linear algebra and in future types of problems that you'll see. Skew symmetric, it's a bit less common, but is definitely something that you want to know and be familiar with before your future studies with linear algebra. So skew symmetric is basically whenever the matrix equals the negative of its transpose. And so what might that look like? Well, let's take a matrix like 0, 1, -1, 0. And let's take the transpose of this. So A transpose is going to equal, so let's take a look at this. First row becomes our first column, second row becomes our second column, 0, -1, 1, 0. You can see that, hey, if I were to do -1 times our matrix, which is a scalar multiplication, that's going to equal our transpose, because this would turn into a +1, this would turn into a -1, and that's exactly what we have over here on the right. So that means that skew symmetric is whenever a matrix equals the negative of its own transpose. Okay, the next type of special matrix that I want to talk about are submatrices, which is pretty. The name kind of explains what it is, but let's just say we had a big matrix here, like something like 1, 2, 3, 4. 1, 2, 3. Actually, it's just fine. 4, 5, 6, 7, 8, 9. So 3 by 3 matrix here. We can take submatrices basically by removing any number of rows or columns from our matrix. And that might look like 8, 9. This could be a submatrix. 4, 5, 7, 8. This could be a submatrix. And the cool thing about this is that we can kind of skip rows and skip columns. So I could say that 1, 3, 7, 9, while it might not look like it, is actually also a submatrix of A, which is a really, really cool part of it. And I honestly just find that baffling that we still consider those submatrices, but it is pretty cool. And one thing that's also very important to note is that A is a submatrix of itself. So if I were to rewrite this whole matrix, that would be a valid submatrix of this, because you can select all the rows and all the columns to remove for your submatrix definition. And so something that we can also do is called partitioning matrices. And so to partition a matrix, you kind of just draw, horizontal lines and vertical lines wherever you want. And this has no impact on the actual matrix itself. It just makes it easier to visualize what parts of the matrix that we're looking at and what are the areas of focus that we need to do. And so this is split it into 4 different sections here. So we have this section, this section, this section, and this section. And our partitions have partitioned our matrix, so to speak. And we call it a partition matrix, obviously. And you can partition a matrix in any way with any number of partitions. I could even make it everything is partitioned, and I have 9 different partitions in our matrix. And this just makes it easier if you use it strategically to visualize the different parts of the matrix that you're looking at and the different parts that you're putting emphasis and importance on. And one thing to note with this is, well, not with this, but in general, is if you have a row that only has zeros, then it's called a zero row. And a non-zero row is going to have a 0 in that row. And you'll see me use this terminology, and you'll see pretty much all textbooks that you'll ever read and all lectures that you'll ever watch use this term to describe matrices that are of importance to us, and or rows that are of importance to us. And so that's pretty important. One other thing to note is row-reduced forms of matrices, which are very, very important for linear equations, or rather simultaneous linear equations. And so row-reduced is basically just whenever, let's say we have, let me switch back to white. Whenever we have something like 1, 2, 3, 1, 5, 1, 4, 5. And then we have zeros here. So a row-reduced matrix is a matrix that the first row will have a 1 in the earliest spot in the earliest column, and then everything in the rows beneath that one column are going to turn out to be 0, like we see here. Okay? And then you have the one here, the second row has the earliest part of the second, and that'll go in the second column, and it's the earliest column for anything below it, and you see how both of these are 0. Another example of this would be something like, hopefully I can find a good one. We could say something like, technically, 0, 0, 1, 0, 0, 0, 0, 0, 0 would be in row reduced form. And so you can see how the first row has the earliest example of a value. And a better one yet, actually, that I just thought of. 1, 2, 3, 0, 0, 3, 0, 0, 0. This is also row reduced because again, first row has the earliest one of the column, and then everything below is 0, and then 3 is on the second row is the earliest, and so on and so forth. And the third row is 0 because obviously we can't have anything. Okay, so there's also something called lower and upper triangular matrices, which is very useful in LU decompositions, which mainly focus on those actually. So we'll cover that in a later video, but an upper triangular matrix is basically just when everything above the everything below the diagonal is 0, and if this were lower triangular, then everything above the diagonal, so all of these would have to be 0, and then these could be whatever. And that would define upper versus lower triangular. Okay? And I think that actually will conclude the special matrices that I wanted to talk about. So let's move on to linear systems, which is going to be actually a pretty big portion of what we're going to study here in linear algebra. So linear systems, let's say we have a very annoying system of equations like 4x minus 7y plus 13z is going to equal 562. And then we also have 7x plus 2y minus 5z equals 737. I don't know about you, but I would not want to solve this ever. So we can use matrices, which are going to be the most efficient method for solving systems like this. And the reason we use matrices are because there are techniques that just let us do hundreds of equations, hundreds of variables so simply and so efficiently. I don't want to actually, I don't know if I should say simply, but just more efficiently. Okay, so how do we represent this system as a matrix? Well, let's say we have a starting matrix, which is going to be A, and then we're going to have X to represent our variables, and then B to represent our solutions. So what does each of this mean? Well, A would be a combination of the matrices of basically all the coefficients in our system. So that would be something like 4 minus 7, 13, 7, 2, Z. That would be A. 7, 2, minus 5, sorry. X would be our variables. So you would have basically just you would basically just have, wait, apologies, you need another equation in this just because it would be infinite solutions if you didn't, because you have 3 variables. So I'm just going to say 5x minus 4y plus 2z equals 345. Okay, great. And then I will erase this, and we will add our new coefficients to A. So this is A. It's just a matrix containing all our coefficients organized like that. And then our variables go in their own matrix, or vector if you would prefer, x, y, z. And then our solutions, 562, 737, 345. And these go in their own matrix. And so this is how we can represent our system in sort of a matrix equation. And then we can also have an augmented matrix. And I didn't go over the term augmented matrix, but that's just basically any matrix that has a partition. And so the augmented matrix for this would be just A and B with a partition in between. So 4 minus 7, 13, 7, 2 minus 5, 5 minus 4, 2. Partition us here. I'll use gray just to stay similar. Gray, and then 562, 737, 345. And that would be an augmented matrix that basically just represents our solutions. And so there's a couple techniques that we'll look at for solving matrices in some future videos. But for this one here, I feel like this is a pretty good introduction and a pretty good spot to leave off on. So hopefully you did learn something in this video and this can be applicable, and this is a very good base for you to build off of. And one thing I want you to practice is just creating these matrices and also just knowing these things, these different types of matrices, partitions, understanding partitions, submatrices, understanding, this is a big one, row reduced, and then also row reduced echelon form. I didn't go over this ladder in there, and it's not as important, but row reduced, definitely understand this, and also just be familiar with it because it will come up a lot in our future videos. But yeah, that concludes this video, and I'll see you in the next.